Hello everyone. In this lecture we are going to study application of MATLAB in control system, that is part 2. In the last lecture we have covered the application of control system part 1, in which we have designed different types of transfer function. We have converted the transfer function into state space and converted that state space into transfer function form. So in this lecture we are going to study the time response of control system, that is open loop response and as well as closed loop response of a system, any system which we want to check. Now first I will discuss some of the different types of uh, input signals which we can apply to any system. So let's start with the uh, different types of input. So we have the first input, which is impulse input, that is impulse, and denoted by del t and defined as del t equal to 1 for t equal to 0 and 0 for t less than or t less than 0 and t greater than 0. So we have del t signal which can be depicted as 1. This is del t and this is the time axis. This is the first signal which we can use in the control system response. Next input is step input. The step input is denoted by ut and it is defined as ut equal to 1 for t greater than or equal to 0 and 0 for t less than 0, and it can be pictorially can be depicted as like this. This is ut and this is time axis. And the third signal is ramp signal. So this ramp signal can be defined as ramp signal. It is denoted by RT and it is defined as RT equal to T for t greater than or equal to 0 and 0 for t less than 0, and it can be pictorially seen as or depicted as like this. Here this is the time axis and this is the RT axis. When time equal to 1, RT will be equal to 1. Similarly, when time equal to 2, RT will be equal to 2. This is the pictorial representation of ramp signal. So basically we can find out the Laplace of these signals for del t. Its Laplace transform is 1. Similarly for ut, Laplace transform is 1 upon s, and that is for RT the Laplace transform is 1 upon s square. So when we have a system, we consider it as a block which is a transfer function, and we can find its response, that is CS, by applying different input, that is RS. RS we can consider here is del t, or either del t ut or RT, and then we can find the response CT of the system. So we already know how to define a transfer function. Now we have to find its open loop response by giving these signals, that is del t, ut and RT. In MATLAB we can find directly the impulse response by passing by using a function that is impulse, and passing this function with a transfer function. When you use this command, this will uh, draw the impulse response of any transfer function or any system. And for step response, there is a command called step, and we have to pass the transfer function tf into that function. This will create, or this will draw the step response, and this will draw the impulse response. So let's try to code some of the examples. So let's start with an example. So we take first example as tf equal to s plus 1 upon s square plus 3s plus 2, and we consider second example as tf equal to s plus 3 upon s cube plus 2s square plus 2s plus 3 multiplied with e raised to the power minus 2s. So we have to draw the impulse and step response. Impulse and step response of these two transfer functions. So let's try to code. So we first define s as a transfer function and will be stored in a equal to tf, and passing s to it. When you hit enter, a will store s. Now t1 we consider here is s plus 1 upon s square plus 3s plus 2. So s is stored in a, so we can take a plus 1 and we put it in bracket divided by s square means a square, in the bracket again a square plus 3s means 3 into a plus 2. When you hit enter, this will store a continuous time transfer function, that is s plus 1 divided by s square plus 3s plus 2. Now we have to find the impulse response. For finding out the impulse response, we have to write impulse and passing this function with the transfer function t1. When you hit enter, this will, I think there is a mistake in the spelling, so impulse spelling is impulse. When you hit enter, this will create the impulse response of this particular system. This is the response, and you can change the accesses as per your convenience. What is the amplitude? Let's say it is in volt, then you can convert it into the volt. Or what is the axis in I think this axis, time axis, will remain the same, and over above you can see here it is written impulse response. So this is the impulse response for this particular transfer function. Now you can easily find out its step response by writing step in passing this transfer function t1. When you hit enter, this is the step response. I hope this impulse and step response is clear to you. Next we will try to code the second example. So let's try to code this second. So transfer function second is s plus 3 upon s cube plus 2s square plus 2s plus 3 multiplied with e to the power minus 2s. So let's try to make this transfer function in T2 equal to s plus 3. We'll put this in a plus 3. A plus 3. This complete is divided by a cube, sorry, in the next bracket, a to the power 3 plus 2 into a to the power 2 plus 2 into a plus 3, when and this whole complete equation is multiplied with e to the power, that is exp minus 2 into a. When you hit enter, this will store the transfer function in T2. Now we can find the impulse response by using the function impulse and passing this function with transfer function T2. When you hit enter, this is the impulse response of the system. Here you can see the output of the system will remain 0 till 2 seconds. Why? Because this 2 indicates here this is minus e to the power minus 2s. This will represent the a dead time of the system. Till that time the system will not respond to any input. So here in this response, the response will be 0 till 2 seconds. After 2 seconds, the response will start moving and give this type of response as depicted in this plot. So we can find its step response also. So for step response, we have to write step and passing this function with T2. When you hit enter, this is again the step response of the system. You can see here that here also the system will remain 0 till 2 seconds, since there is a 2 second of dead time in the transfer function. So system response is 0 till 2 seconds. After that system response will rise, and this is the transient part. And further later in the after 40 seconds the response will start settling to its normal value, that is 1. You can see this figure here. After 40 seconds, around 40 seconds, the system response starts settling to its reference value. I hope these impulse and step response are clear to you. Now next step is we have to find the ramp response. So there is no specified function in MATLAB to draw ramp response. So we have to modify our equation as accordingly to draw the ramp response. Now we can modify the equation for finding out the ramp response of any system. So let's consider a transfer function. Transfer function, which is I will show in a block. Let's take, this is the transfer function of system for which we have to find the ramp response, that is RT. We pass here RT and we find out CT of the system. RT will be represented as R of S, that is 1 upon S square. So we break this into two parts, that is 1 upon S into 1 upon S, and we pass this 1 upon S with transfer function. So we convert this as like this: transfer function multiplied with 1 upon s, and this is ct, or we can say that cs, and here one part is remaining for the input, that is 1 upon s, and this is for, I think, ut. Ut have Laplace transform 1 upon s. So we converted this equation 1 upon s square, that is for ramp signal, into two parts, and we transfer first part inside this transfer function block and multiplied with transfer function directly, and we will calculate the step response for this particular transfer function. This particular transfer function step response will be equal to the ramp response of transfer function itself. So let's try to find the ramp response by using step command. So we will directly find out the ramp response for this particular transfer function, which is t2. Now we have to first multiply this transfer function t2 with 1 upon s. So we have already stored s in a, and we have already designed t2. Now we consider a third transfer function, that is t3, that is equal to t2 multiplied with or divided by directly with a. When you hit enter with this, a t3 will be formed, which is this given in equation. So you can find this, find the step response of this t3 transfer function. This will be equivalent to the ramp response of t2. So let's try to find step of t3. When you hit enter, and this is the ramp response, it will look like a straight line. I hope this ramp response is clear to you. Now let's try to practice some examples. So let's try to practice one or two examples. Now I have considered two examples, that is we have given t1 and t2. Now we have to find the step, ramp and impulse response of these systems. So let's try to code for these two systems. So first I will clear the workspace and clear the command window as well. So first I will define a variable a, which is store transfer function, that is s only. Now we can find out this t1 by using this a variable. Now that is 144 divided by a into a plus 6 into a, sorry, 12 into a plus 144. When you hit enter, this will store the transfer function t1 in. Now we can find easily the impulse response by writing impulse and passing this with t1. When you hit enter, this is the impulse response of the system. Now we can also find step response with passing this t1 transfer function to step function. This is the step response. I hope these two responses are clear to you. Now we can find out the ramp response. Now ramp response can be found out by using that transfer function divided by that variable a. So we can directly write step and passing a transfer function t1 divided by variable a as stored in as a stored as, and we have to convert this transfer function into t1 divided by s. So this fulfills our requirement, and this will draw the ramp response. And this is the ramp response. You have to change this, as here it is shown step, but it is the ramp response of the transfer function t1. So you can change it by simply clicking on this particular I think there is here you can write ramp response. I think this is not changing, so here you can change, you can write ramp. I hope this ramp response and how to generate the ramp response using step command is clear to you. Now let's try to code for the second transfer function. So second transfer function is s plus 4 divided by s square plus 6s plus 9 multiplied with e to the power minus 3s. So here we use t2 equal to, in the first bracket I will type s plus 4, and first I will multiply this with e to the power, that is exp minus 3s minus 3 into now sorry, we have to pass here a, as s is stored in a, minus 3a, and this whole is divided by a into a plus 6 into a plus 9. When you hit enter, this will create the continuous time transfer function t2. Now we can easily find the impulse response passing this impulse function with input argument t2. When you hit enter, this is the impulse response of this t2 transfer function. You can see here that from 0 to 3 seconds the output of the system will remain 0, as this transfer function contains dead time of 3 seconds. So I hope this impulse response is clear to you. Secondly, we have to draw the step response by passing step function with this transfer function t2, and this is the step response. Here also you can see that output remains 0 till 3 seconds. Now for ramp response we have to use a step response and passing this t2 divided by this a, which is store a store s. So t2 divided by s, and passing it with step command. When you hit enter, look at here, this is the ramp response. In this response also the output will remain 0, output of the system will remain 0 till 0 to 3 seconds. You can check this by zooming the graph. You can see here that output will remain 0 till 3 seconds. This is due to the dead time present in the system. So I hope these two examples are clear to you. Now next is we can find out the response of the system for any input, for any type of input by using lsim command. So let's try to study that and try to code for these two transfer functions. Now the command for uh, finding out the response to any arbitrary input is lsim. That is lsim, and passing this function with transfer function, that is n comma d, that is numerator denominator matrix, and u, that is the input which we want, which for which we want to draw the output response, and time t for seconds, for the duration of which we want to draw the response. So let's try to code for this particular transfer function t1. So I will try to code for this t1. I will first remove the command and this block. So let's try to code for this two transfer functions. These are already stored in t1 and t2, as you can see in workspace. So we will first define the input. So let's take input. Let's take first time t equal to from 0 with an increment of 0.1 till 10 seconds, and we'll store this in t. And now we take input u equal to sine of t. We want to draw the response of these system for sine input. When you hit enter, you will store. So first clear out the screen. Let's pass this u sine t and put colon. Now we want to find out the response for this sine signal. We have to use the command lsim, passing this transfer function t1 with input u and time t. When you hit enter, this is the response of the system, as well as one is the response and other is the reference signal, that is sine t, is drawn over here. So let's first I remove this block, then I will show you the result. This is the result. Now we can modify this figure by clicking this, and first I will put this legend. I think t1 is the your response of the system for the sine x, and this is the input. I think the selected one is the input, so we can change its color. For the input, I think we cannot change the property. For the output we can change, so we can change the color first to red. The line width will consider 2. This is the response for this particular sine signal. You can change the excesses also, and this title of the figure as well. So this is for response for I think sine x or sine t. I hope the response for any system for any arbitrary input, we can use lsim command, and I hope this is clear to you. Let's take any other example which will clear the concept. Now these are the two examples for which we have to find the response of the system. For first input is, that is, e to the power minus t, and the second input is cos t. So let's try to code and try to find the response of these two systems for these two inputs. Uh, so first clear the workspace and clear the command window as well. So let's try to code. So first we have to define a with a transfer function that is stored as. Now we can define this transfer function t1 equal to a plus 2, put this in brackets, divided by a square plus 3s, or that is 3a plus 6. When you hit enter, this t1 will be created, or that is transfer function 1 will be created. Now you can find the response of system for exponential input and for cos t. So let's take time first. So we define t equal to 0 till we take increment of 0.1 till 10 seconds. When you hit enter, this will store t. Now define first u1 equal to exp and passing with minus t. When you hit enter, this will store u1 and u2 will be equal to cos of t. I hope this t, u1 and u2 will be created, and we have to draw the response for this t1 for input u1 and u2. So let's try to find out the response. So we have to use the command lsim, passing this transfer function t1 first. Then we have to use the input u1 first, and then the time vector for the time instant, which we have to draw on the time axis, that is the x-axis. So when you hit enter, this will be the response of the system for this exponential input. I hope this exponential input response is clear to you. Let's try to code for cos input, response of the system for cos input. For that we have to use the same command and change this u1 with u2. So when you hit enter, this is the response of the system for open loop, not the closed loop response. These all are open loop response. So this is the open loop response of the system for cos signal, that is cos input. Now let's try to code for the second transfer function. Input is already stored in u1 and u2, and time is stored in t vector. So we have to define only the transfer function t2. So let's first clear this command window. Now we cannot clear at that time the workspace, because some of the variables which we need are stored in workspace. So at that time you should keep these variables in workspace. So let's make this transfer function t2 equal to 10 into a into exp minus 3s, 3 into a, sorry, and divide this whole is divided by is complete is divided by S, that is A into A plus 7 into A plus 6. When you hit enter, this will create the transfer function second. Now you can easily draw its response by using LSIM. Here you have to change first T2, and for the exponential input you have to convert this U2 into U1, and when you hit enter, this is the response of the system for exponential input, decaying exponential input. So I hope this response is clear to you. Now let's try to find the response for cos input, and this is the response of the system for cos input. Here also you can see here that the response of the system will be 0 till 3 seconds. Why? Because the system contains a dead time of 3 seconds. I hope this is clear to you. Now there is one more way you can find out the response data as well. So you have to use this square bracket and use this y comma t, where y is the response in time domain and t is the time, which will be same as this t. So you have to pass this with LSIM, transfer function t2 comma u2, passing this time t. When you hit enter, I hope this t and t is the time till 10 seconds, that is same, and this is the y data, that is the response of the system, will be stored in y. Now you can simply find out the different different performance indices by using a command, that is step info. In that case you will find out the rise time, peak time and settling time by using the command step info and passing this vector y comma t. When you hit enter, this is the rise time. You can see here is 0.0304, settling time is 9.9757, and overshoot is 331.2428, undershoot is 401.4768, and peak is 1.1641, and peak time is 8.7. So you can find out the performance indices that are I think delay time, rise time, peak time, overshoot and settling time. All this can be found out using step info command. So you need the data for generating this step info values, that is the performance indices values. That's why I use this particular command y comma t equal to LSIM t2 u2 comma t. So I hope all this is clear to you. For state space, you can directly convert the state space into transfer function, and then you can find out all the responses. This is the method which you can use for state space when system is represented in state space form. So I hope all these are clear to you. So thank you very much.